Hello everyone, WABYA here, May 16th, 2017, and I thought we would have just a little bit of fun measuring things like SWR using a couple of different instruments. We're going to be measuring a 2-meter Yagi antenna. There we go. You'll have to forgive me as got the sun right in my eyes. It's kind of hard to tell if I'm even close to showing the antenna, but I think I got it. So that's a 17 element Cushcraft. It's at 85 feet, fed with 7/8 hardline. There's about 200 feet of it. It goes back to the shack. So we're going to be measuring SWR using 4 basic instruments. We're going to be using a Bird 43 watt meter. We're going to be using a AIM-4170C network analyzer. We'll be using my Siglent spectrum analyzer with its dedicated reflection bridge, which is a very, very cool gadget. And then we'll be using a real vector network analyzer, an Agilent 8712ES. So let's get down into the dungeon and we'll start making some measurements of this antenna. Okay, WABYA, we're back inside now and we're ready to start making some measurements. We'll try to make this as quick as possible. So what we've done is we've taken a short jumper of LMR 400 coax. You can see that coming in through the bulkhead panel, going directly into the Bird 43 watt meter, and it's being driven by, in this case, the Flex 5000. It's got the internal VU module that lets me operate on 2 meters and 432. I've brought up Power SDR console. I've set it up for 2 frequencies. We're going to be transmitting a signal at 144.150, which is a typical meteor scatter EME weak signal frequency. And then we're going to be putting a signal in at 148.85, which seems to be a very low SWR frequency on this antenna. So we're going to collect data at 2 frequencies. So we're going to first measure the forward power. We're using a 100 watt slug here. Probably going to be putting 50 watts out of the radio to measure the forward power. For the reflected power, I'm going to substitute a lower power slug, same frequency range. It'll help us get a little bit more accurate reading. Of course, any forward power and reflected power measurements are only going to be as accurate as the calibration of the slugs and the meter, and in this case I have not verified either one, so I'm going on faith that the slug is accurate, this one and that one, and that the meter is fairly accurate. I have fairly good confidence in the meter since I've got 3 or 4 of them and they all read identical. As far as an absolute accuracy goes for the power measurements, I don't have an accurate way to measure, say, to an absolute level of 1 watt or so when I'm putting out 100 watts, for example. Just don't have that capability. Even with a high-end spectrum analyzer and network analyzer, the difference of half a dB or a dB can equate to quite a few difference in watts which would make it difficult to validate the accuracy of the slugs. So what we're going to do is take a measurement forward and reverse using the Bird 43, and then we're going to hook up that antenna directly to the AIM-4170C network analyzer. We're going to have to use a PL259 to N adapter, but that shouldn't have much of an impact on our measurements here at these frequencies. We'll use a good quality Amphenol type adapter. And then for our next measurement, we'll use the Siglent spectrum analyzer, and this is my Siglent 3021X, which I'm still very much in love with. Really enjoy this spectrum analyzer. You cannot beat it for value as far as price and what you get. I went ahead and purchased the dedicated reflection bridge. This is a directional coupler that is specifically made for this spectrum analyzer. What it does is it couples the tracking generator output and the spectrum analyzer input directly to the coupler. It's spaced perfectly so that you don't have to use any coaxial cables. It comes with a pair of high quality end-to-end male adapters. Comes in a beautiful case. The bridge and the coupler is extremely well made, very high quality workmanship. It's a fine addition, and it's really good for making fast measurements of the return loss, or the SWR, of an antenna, which we'll demonstrate here shortly. And I've already set up the spectrum analyzer in the mode to show return loss and SWR at our two frequencies of interest. So right now, of course, with nothing connected to it, it's showing infinite SWR. And then finally, we're going to hook up that antenna to a true VNA, vector network analyzer. We've done the same thing. We've set up the frequency to start at 140 meg. We're going to run it up to 150 meg. We've set up a couple of markers, and we'll see how all the different instruments compare. So first the Bird, then the AIM, and then the Siglent spectrum analyzer with its dedicated bridge, and then the Agilent 8712ES vector network analyzer. So let me go ahead and take some measurements. We'll document that and see what we get. Okay, so first things first, let's go ahead and put a carrier out at 144.150. We'll put the radio in the tune mode, and we'll see what the Bird registers. And we'll see it's right at about 50 watts. I've preset the power output on the flex so that it's a nice easy number to remember. So that's 50 watts forward. Okay, so I just realized, made a small mistake. Our maximum frequency on the 2 meter band is 148 megahertz, so I'm not going to be able to transmit a signal on 148.850. We can make SWR measurements with the other instruments, but I'm not actually going to be able to use the Bird to transmit a signal. So for the Bird 43, I'm going to transmit at 147.995, which is about the highest I can go legally. And we'll see what we get for power reading. So if we zoom in on that, we get right in front of the meter. You see it's pretty darn close to 40 watts. And we'll go ahead and make a note of that. Okay, we've put in the 25 watt slug. We've got it set up to measure reflected power. We'll go ahead and throw the same carrier output. And we note that power output is just under 2 watts. Each division is about half a watt. So it looks like we can call that about 1.8 watts reflected. This is at 147,995. Okay, now we're set up at 144.150. We haven't changed the power output on the radio. We'll go ahead and throw the same carrier. We're still using the 25 watt slug reflected power mode. Remember, each division is about half a watt. So we see that's about 3/4 of a watt. We'll call that 0.75 watts reflected. Okay, next step is to use the forward and reflected power readings and go ahead and calculate the resulting SWR. It's very easy to do by hand calculator, but since I'm lazy, I like using a lot of the online calculators that are available off the net. So all you do is enter in the forward and reflected power, hit calculate, and you get your answer right there. Get a resulting SWR of 1.54 for that frequency. So I went ahead and did that for our 2 frequencies of interest, and went ahead and documented that on a piece of paper, and we'll move on to some measurements using the AIM network analyzer. Okay, so I've gone ahead and connected up that same jumper. We're using a small PL259 to N adapter going directly into the network analyzer. The AIM is computer controlled, and I have the console pulled up on one of the monitors here, and I had it sweep from 140 to 150. You can see here why I originally was going to pick the 2 frequencies to be 144, 150, which is where this blue vertical line is. That's where that marker represents, right there. And then why I was going to use 148, 850. Turns out this antenna, the 17B2, in my particular case, has a really low SWR way up there, so I was going to measure it using all of the instruments at that frequency. We can do so on the network analyzers, but we couldn't on the bird because we can't legally transmit up there. So what I could do is take all the measurements up here at 850, except the bird 43, but I thought since a lot of hams like using watt meters, especially the bird 43 for power and SWR calculations, it might be best if we move our frequency just down below 148, which would put us up in this range right here. So you'll note that the SWR won't be extremely good. If we move across here, we can see I've got the AIM set up to display SWR along the y-axis, and it goes from a 1 to 1 up to a 1.9 to 1. So 1/10 of a SWR unit per division here. So you can see it's got a nice dip just down below the band. If you're a Mars operator, this would be ideal, but still fairly low where I operate at 144 or 150. And then it's got another dip outside of the band at 148.850 roughly. So let's go ahead and look at the data. First thing we notice, at my marker frequency, a 144.150, we have an SWR of 1.17. So we'll go ahead and make a note of that. And then the AIM has a really cool feature. It goes ahead and calculates what the minimum SWR and frequency is. In this case it's 1.12 at 148.820. The other day it was at 850, today it's at 820. But I've rotated the antenna somewhat and it's pretty windy out there, so things may have changed just a little bit. But that's only off 30 kilohertz, so really no big deal. I've also gone ahead, what's really neat is we can have the AIM plot out the return loss, and it's done so here on the scale directly beneath the SWR. So I'll go ahead and document these values, and I'll add it to my Pigeon Scratch notes here, which we'll summarize after we take all of our measurements. So I thought it would be beneficial before we move off of the AIM to do a real quick test. This is something that I like to do to verify that the instrument is providing accurate data. What I've done is I've taken two precision 50 ohm loads. These are good to 18 gigahertz. They have a very close impedance to 50 ohms exactly without much reactance. And what I've done is I've put two of them in parallel to make a 25 ohm load and put it into the AIM. And I've gone ahead and you can see here on the AIM over our frequency range that in fact it is showing a 2-to-1 SWR from 140 to 150. So that's should give us a warm fuzzy feeling that things are working the way they should be. And if we look at the return loss, we can see that the number is about, it's kind of hard to read, but we can call it 9.6 thereabouts, 9.6, 9.7 dB. So we get the SWR and return loss. And as a very quick verification, they don't make these anymore, but they're very cool if you can find one. This is an old antique HP slide rule. Very handy device. What you can do is enter in the return loss. In this case I entered in about 9.6 or so dB, and then you can look up the standing wave ratio and it corresponds to 2-to-1. So the numbers from the AIM in fact correspond to what the math says it should be. So I feel pretty confident that the measurements we got from the AIM are fairly close. So now let's go ahead and move on to the Siglent. I'll go ahead and do the same exact test. We'll put the 25 ohm load on the reflection bridge, and then we'll also do the 2-meter antenna over the same range, 140 to 150, and we'll see what we get. And then as a final test, we'll put it on the Agilent real network analyzer. We'll see what it says. Okay, we're back and we've got the test load right there connected up to the reflection bridge. Dedicated Siglent reflection bridge. Should be presenting a 25 ohm load. We've got the sweep running from 140 to 150 meg, as shown right there. I've got the return loss on the y-axis, 2 dB per division, and we're getting pretty consistent results. 2 markers set up, one of them at 144, 150, the other one at 147,995, and we can see that the numbers are very close to what we measured on the AIM. We're getting a return loss of about 9.7 at one frequency and about 9.8. Average it out, if you will. So I really like that. SWR is very, very close to 2 to 1. So I feel pretty confident that we're going to be able to make some accurate measurements using this beautiful bridge. So let me go ahead and connect up the real antenna. I'll document these numbers just for safety in case we need to recall them. We can look them up here on the scratch pad. Let me go ahead and hook up the real antenna and we'll take some measurements. Okay, we've got the LMR 400 jumper connected directly up to the reflection bridge. I've gone ahead and changed the y-axis. I'll zoom in here a little bit. Hopefully it won't be too out of focus. I changed it to 5 dB per, and what we're looking is the return loss here. And again, we're sweeping from 140 to 150 meg. Got my 2 markers set up here, 144, 150, and in this case 147,995. What I actually should do, let's set up a 3rd marker and let's make it 148.82 megahertz. There we go. I got a bad glare there. Let me stand up. So there's our 3 markers, and here's the resulting data. I'll slowly zoom in. We can see the return loss numbers. About 19.75 if I had to. It's toggling 20 every once in a while down to 19.5, so I would kind of average that out to 19 3/4. The other one we could almost call 12 dB, and the bottom one, excuse me, we could probably call pretty close to 26 dB. Resulting SWRs are over here. We can call that 1.22 roughly, 1.65 roughly, and we can call that about a 1.1. So you can see how handy the spectrum analyzer is with this dedicated bridge. What makes it so powerful is that it's rated to go from 1 meg up to 2 gigahertz, and that matches nicely the frequency range of the spectrum analyzer, which means you can analyze any antenna system and get this kind of data in a split second. The AIM, on the other hand, is not an inexpensive item. It runs about $600, but it only goes up to about 170, 180 megahertz. So it's very useful, very handy, very accurate, but it's very limited in its frequency range. With this instrument right here, you can take this kind of measurement over an incredibly wide frequency range. What I did notice about the bridge, and I'll make this comment, when the load impedance starts to be highly complex, highly reactive, and you start getting into higher SWRs, especially at the higher frequencies, you can start noticing a deviation from the theoretical values, or what it should read and what it's actually reading. And that really has to do with the fact that the coupler, the directional coupler that's used there, really could use more directivity. Put it bluntly, I think the directivity is only rated for about 20 dB, and it really should be a little bit higher if you're going to get accurate measurements for complex loads or loads that present a higher SWR. But for most practical applications, it'll do just fine, and especially for finding the resonant frequency of antennas or tuning antennas, things like that, looking for dips, you can't beat it. It takes just a few minutes to set up. Literally, I had this set up from ground zero to this display in less than 1 minute. Of course, let the instrument warm up prior to this, but the actual setup was less than 1 minute. So very, very powerful, very cool device, and an excellent combination. So now that we've got our data using the spectrum analyzer and bridge, let's go ahead and see what kind of numbers we get with the dedicated VNA. Okay, we've got the Agilent 8712ES running. It's sweeping from 140 to 150 meg, and I've got the same exact test load connected, 250 ohm DC to 18 gig terminations in parallel in an Amphenol T adapter, and I've got it set up to display SWR along the y-axis to make it convenient, and I've got 3 markers set up, which we can see here. Those are the resulting SWRs. So we can see that at least 2 to 3 hundredths of a dB, it's reading 2 to 1. So I trust that my calibration of the VNA was accurate. I use a NARDA open short load to do the calibration. There's going to be a slight error introduced because this is a DIN open short load. So there's a small adapter here, N to DIN adapter, and that is going to introduce some errors. But for the frequencies that we're dealing with here on 2 meters, that shouldn't be too much of a problem. So I'm fairly happy with the results that I see here. Let's go ahead and connect up our 2 meter antenna and see what we get. Okay, so I've gone ahead and connected up the same LMR 400 jumper I am using a small Amphenol elbow that I've been using on and off, just like we were with the Siglent spectrum analyzer and reflection bridge. And we can see the SWR curve looks extremely similar to what we saw in previous measurements. You can see here why I wanted originally to go at 148.82 or 85, because that is this antenna has an interesting low SWR point. Bottoms out at a 1.1 to 1 at way up there, but it also has a good low SWR where I operate down at the low end of 144 meg. So that's what the SWR curve looks like. I've set up our 3 markers, and here's the data for the 3 of them. So I'll go ahead and document that on my back of my napkin here, and then we'll see what the results are for all the different instruments. One thing I forgot to do here, we're showing SWR here. I wanted to document the return loss numbers, so let me just very quickly hit format. There we go. So here's the actual return loss measurements. And that's what the resulting plot looks like. Of course, it's going to be very similar to the SWR plot, but the numerical data is going to be different. So I'll go ahead and document that on our data sheet here. Okay, so how did we do? We took a measurement with the Bird 43, the AIM network analyzer, the Siglent spectrum analyzer and dedicated reflection bridge, and a true vector network analyzer. Went ahead and summarized the results on a little scratch piece of paper, and I think we did pretty good. We can see down at the low frequency 144.0150, the Agilent and AIM are in very close agreement, within 1/100th of a dB as far as SWR. The Siglent at 1.22 is definitely very close to that. Remember, reads a little bit high, and the Bird 43 at 1.28 was slightly higher than that. So looks like the 2 network analyzers seem to be in very close agreement with each other and provide the lowest values of SWR, probably the most trustworthy. As we move up to 147.995, the SWRs are very close all the way across. 1.59 for the Agilent, 1.56 for the AIM, 1.54 for the Bird, 1.66 for the Siglent, and then way up at 148.82 the SWRs for all 3, for all practical purposes, are exactly the same. I mean, within 1/100th of a dB, which is probably not even repeatable. I wouldn't, I'm just writing it down, but really isn't necessary. It's not accurate. You could really say the SWR is a 1.1 to 1 at those 3 frequencies. So there you have it. That's the results using 4 different instruments on a real antenna, and I hope you found the video useful. I really recommend if you have the Siglent spectrum analyzer, by all means, and you like goofing around with antennas and building them, tuning them, maximizing their performance, by all means get the reflection bridge there. Very, very well made, and it's a fine addition to the analyzer. So 73 from WABYA.